on Kurt's program, which is that on all of them, they have slightly different inputs for data. So that question was a really good one. All of his programs, except for the data reduction program, are compatible with anyone's data, right? So the data reduction is specifically data coming out of our lab, but for any of his other programs, you can put anything you want in there. Just look at how he's formatted his Excel sheets, format them in the same way, and you're good to go. But somebody had asked about data reduction, so.
Yeah, on that point, so if you go to the GitHub page, in the latest releases on GitHub, I always include an example or a few examples for each. That's usually the hurdle that I run into when using it. How do I just make it do the thing? How do I just put it in? So there's examples for everything. If you don't find it, you know,
It is absurdly cold in this room. Okay. Okay, so we're going to switch here one more time. This is the final module, and then we're going to have a little wrap-up discussion. But this is something that I think is really cool, and I'm personally really excited about. So it's looking at trace and rare earth chemistry in zircon. And so we started out the day, we were talking about zircon, right? Zirconium, silicon, oxygen. We measure those isotopes, or we measure those things. We measure some uranium, thorium, lead for ages. We talked about lutetium, ytterbium, hafnium for hafnium isotopes. But hey, there's this whole other playing field on our elemental chart, right? So we've got the lanthanide series down here, are rare earth elements. We've got light rare earth elements, middle rare earth elements, heavy rare earth elements. We've got a ton of trace elements over here, all these pink squares. So just tons that we could potentially do. And it's largely on us to figure out what to do with them now. So I'm going to give you guys a bunch of examples, but there's so much more space to work with here. And I guess that's really what I want you to walk away with. Okay, so a bit of like background on zircon, which maybe we should do first thing in the morning, but we do not. So zircon is a tetragonal orthosilicate. It has an 8-fold coordination site and a 4-fold coordination site. In the 8-fold site, we get zirconium 4+. In the 4-fold site, we get silicon 4+. Turns out things like hafnium, thorium, uranium fit really well in that 8-fold site. So they substitute in readily, they're lattice bound. Things like titanium can squeeze their way into the site. They don't always fit, depends on the ionic radius, which is actually, as it turns out here, can be a temperature controlled process. So titanium will sometimes substitute into the site, and the amount of substitution we get is temperature controlled. So we actually have a thermometer in zircon, which is kind of cool. All of the other trace and rare earth elements that we're talking about, I guess rare earth elements, most of them exist in 3+ valence states. So does yttrium. The exceptions to that would be cerium and europium, which can also have other valence states. So if they want to get into the crystal lattice, they need to come in by a coupled substitution, which is usually accommodated with phosphorus. So 3+ plus 5+ equals 8+, which is the same as 4 + 4. Okay, so because of Goldschmidt's rules, everyone falls back sort of to earth materials, and they remember that, okay, so we need something that has a similar size and similar charge to get into the crystal structure. So it turns out that heavy rare earth elements, they have a similar ionic radiance, so they substitute readily into zircon. Light rare earth elements are relatively incompatible because we don't have the right ionic radius. Cool. Okay, Kurt mentioned Bellisova before. This is from one of her other classic papers, Bellisova et al. 2002. Here she's gone to all of these different locations around the world, sampling different rock types and characterizing zircons for their trace element chemistry. There's a couple of things to take away from here. It's a pretty busy plot. First of all, she normalizes them, so zircon to chondrite. That's the same kind of normalization that we saw before with hafnium. So we like to normalize a lot of geochemical ratios. So anything that is above 1 here is going to be enriched in zircon relative to that chondrite. Anything less than 1 is going to be depleted, right? So things like thorium, uranium, hafnium, lots and lots in the zircon lattice. That makes sense. It fits really well. Other things that we get a lot of are these heavy rare earth elements, not so much on the light rare earth element end. Okay, this slide is kind of a legacy slide handed down from these guys, but I think it's a great depiction of how we can start to think about these processes. So if we take, so these are rare earth spider diagrams going from light rare earths to heavy rare earths. And basically, here's a typical garnet spectra where it's got lots of heavy rare earths, not a lot of lights. Here's a typical zircon. If you're growing your garnet and you're growing a zircon at the same time, that garnet is going to win out. It's going to suck up all of those heavy rare earth elements, and you're going to end up with a zircon that is depleted in those heavies. Okay, so these rare earth element patterns are a function of rock type, which we kind of saw with Bellisova. They're a function of cogenetic mineral phases. They're a function of chemistry. They're a function of pressure, temperature, all the things we would expect. So we can do the same game if we're crystallizing plagioclase. Plagioclase typically has a really positive europium anomaly. If we start breaking down plagioclase, growing zircon, we would expect to see kind of a positive europium anomaly. So knowing something about other phases that could exist at the same time, that could grow at the same time, is going to be really helpful in interpreting trace element data. So we talked about this only very briefly at the beginning of the day, this idea of limits of detection. So just because you put something in a mass spectrometer doesn't mean that your mass spectrometer can resolve it, right? You have to have enough signal that it can actually see that there's signal there, that it's not all under backgrounds. And so on laser ablation mass spectrometers, this turns out to be about 0.1 ppm. And this isn't a big deal for uranium, thorium, lead, because we have tons of that in zircon. So we're not really worried about limits of detection. But now we're dealing with, what do we call them, trace elements. And guess what? They exist in trace abundances. And so this becomes a lot more important, right? So things like lanthanum, maybe we can resolve it, maybe we can't. It depends on the day. Praseodymium, same thing. And so going to labs, you need to know how well each lab that you go, like what your lab can actually resolve on these things. So we think that in our lab, we do well resolving lanthanum, not so well doing praseodymium. Okay, how can you measure these things? We've heard about a lot of these before. So we can do it via laser ablation. We know this game. We can either do it first on uranium lead, and then we can measure our trace elements, or we can actually measure them simultaneously. So we have a split stream tube. We have a tube that comes out. So we have our sample chamber. Tube comes out, splits in two. Half the signal goes to one mass spec. That's measuring age. Half the signal goes to another mass spec. That's measuring trace elements. So that's one way we could do it. We could do it via solution. I don't want to dissolve microzircons, but if you want to do that, go ahead. Good luck. We can do it via our SIMS or our shrimp that we talked about before, or an electron microprobe. Electron microprobes are not, they're not going to get down to the lower abundance trace elements. They're not going to be able to resolve it. If you have low trace element, low abundances, low concentrations, it's just not going to happen on an EMPI. So laser ablation is probably the simplest way to go, but if you aren't concerned about your super trace elements, you could get away with EMPI. Okay, one of these big bag standard slides. What do we do? How do we measure it? I don't want to go into this in too much detail. The key thing here is you need good standards. You need zircon standards. You can't do this with a glass. You need to do a normalization. You need to make sure that things that you're measuring don't have interferences. This turned out to be a really big problem in mass spectrometry. We'll come back to this at the end, and I'll kind of highlight the ones that we have trouble with in our lab. And then the data reduction can be quite arduous. Typically, it's done in iLite. We have an in-house routine that is still in Excel, but Kurt has coded it in MATLAB, so we're getting there. So that will be available soon. So I mentioned that we normalize these things. We normalize them to chondrite. We've heard about kind of this idea before. The reason we do this, if you plot up a zircon just based on its trace element composition, its concentrations, you'll notice that it's super spiky. You guys ever heard of the Otto Perkins effect? So things with odd atomic numbers, they have that loose proton, right? We don't like loose protons floating around. Those usually get paired up. So even atomic numbers are more common in the universe. So we don't like to look at data that looks spiky like this. It's not pleasant to look at. It's complicated to read. So we just normalize it to chondrite, smooths things out. So most of the data that you see published will be normalized or chondrite. Okay, so what can you do with your trace element data? This is, I think, really, really neat, and there's so many opportunities here. And we'll try not to gush too much. So one thing we can do is discrimination diagrams. We can plot our zircon with respect to known compositions of zircons and see, hey, got this detrital zircon. It's 140 million years old. Did it come from a continental arc? Did it come from a basalt that's producing zircons for some reason? What kind of rock type did it come from? These discrimination diagrams can also be used to get back at, say, tectonic setting. Talk about that a little bit. We can do a whole bunch of fancy stuff with mineral melt element partitioning, so partition coefficients, and get back at whole rock values. And we'll talk about why that might be useful. We can look at growth of cogenetic phases, right? Whether if there's monazite growing, that's going to control our thorium uranium ratios. If there's garnet growing, that's going to control our heavy rare earth abundances. And then diffusion studies, which I'm going to completely ignore because I know nothing about. Okay, so discrimination diagrams, coming back to this Bellisova paper. Here's just some examples of this. So she's just taken a bunch of different trace elements and cross-plotted them against each other. So if you were interested in, say, distinguishing between a cyanite and a kimberlite, okay, yeah, you could probably tell the difference on these things. If you were interested in telling the difference between a lamprolite and I don't know, one of the other guys that's plotting in the same space, maybe not so much. So picking the right discrimination diagram for your question is going to be critical. We can also do this for thinking about rock type in terms of whether it's a paraluminous or metaluminous melt. So Trail et al. 2017 showed that the aluminum content of zircon correlates with its original rock melt type, whether it's paraluminous or metaluminous. We can also do discrimination diagrams for tectonic setting. I have a note up here. Beware, with laser ablation, we have interferences with scandium. So I keep getting emails, my trace element data looks great, love this scandium discriminator. We do record scandium in our lab, but that's not going to be a great discriminator for you because that's basically, there's an interference there as well. So, but there's lots of other possibilities here. So here they're plotting iodine ytterbium and scandium ytterbium, and they're basically breaking out continental arc versus mid-ocean ridge type sources based on these zircons. Turns out this spread is essentially controlled by the impact of fractionation based on the crystallization of these other phases, so titanite and amphibole. So depending on what you're crystallizing, you get different spread. So here's a quick example from our lab, kind of in the early days. So we do use, I mentioned don't use glasses. We do use a glass. We use this as kind of a long-term monitor of how we're doing in our lab. So this is a NIST glass. It's doped with a bunch of trace elements. And so we know those concentrations, so we can measure this to monitor kind of how our mass spec does through time. And so what you see is all of these purple are NIST. The white line in the middle is the known value. So we're doing pretty well. Same thing, this red swath is 91500, which is a standard. The white line is the known value. And then we've done 3 different rock types, a diorite in blue, a gabbro in black, and a tonalite in green. You can already see that there's some spread in trace element space. So you could cross-plot these however you wanted to, whatever trace elements versus whatever trace elements. And it's pretty clear in this case that the europium and cerium concentrate anomalies are different for these guys. Turns out these europium and cerium anomalies often have to do with completely blanking here. So europium and cerium anomalies typically have to do with like how the melt is behaving and oxygen fugacity and things like that within the melts. So this can actually tell you about melt mechanics. This spread could be really useful if you were looking at a detrital data set and you wanted to ask yourself, hey, again, I have a tonalite, a diorite, and a gabbro. They're all 1.4 GA. They could all have zircons that I'm looking at. Where was it coming from? You can use it for that kind of stuff. Okay, so this is something that Jay Chapman put out in 2016, and I think this is really, really cool. So typically, the way that we go from trace elements in a zircon or any mineral back to whole rock is using constant partition coefficients. So you guys remember D, basically the how much is going to stay go into the zircon versus stay in the melts. That's that ratio. We typically assume that these are constant. What Jay has done is he's just added some exponents, and this is he's basically made it so that it's not fixed, but that it's dependent on how abundant something is within the melt in the first place. And so this black line here is the measured bulk rock value. So that's what we should be correcting back to. And these red bars here are just individual zircon crystals. So using the old method, not a very good job of reconstructing that black line. Using this new method, much better job. Okay, so why in the world would you want to get back at whole rock values? That's like seems a bit weird. You've got zircon. Well, here's one reason you might want to get back. So it turns out that in whole rock, we can use things like the lanthanum and terbium ratio to get an inferred crustal thickness through time. So this ratio, lanthanum to terbium and strontium yttrium, those are the 2 ratios that are, I guess, most commonly used. They basically rely on the abundance of cogenetic mineral growth, right? So in a thick crust with high lithostatic pressures, you're going to be crystallizing phases like garnet and amphibole. And phases like garnet and amphibole really, really like heavy rare earth elements. So that's going to be sequestered in our amphibole and our garnet, and that zircon's never going to skip. In thin crust, where we don't have garnet and amphibole, those heavy rare earths are going to be available for take-up. We're also going to be crystallizing other mineral phases that actually like rare earth elements a lot better. That kind of makes sense? So we can use ratios between heavy rare earth elements and light rare earth elements to get back, well, to say something about crustal thickness. So that's what this study did, and they did this in quaternary arc systems, where we know the MOHO depth based on tomography. So they can go measure the lanthanum terbium ratio of a quaternary basalt at the surface. They can take a screenshot essentially of how deep the crustal column is using tomography, so just seismology, right? And then we can make an empirical calibration. So that's all they've done here. So here's the logic chain. If we can take a zircon, we can measure the lanthanum terbium ratio. We can get back to whole rock. Maybe we can get back at crustal thickness. That makes sense? And guess what? We also have a chronometer because we're also doing uranium lead. So all of a sudden now we're doing crustal thickness, uranium lead, and we can reconstruct potentially crustal thickness through time, which would be really cool, right? That gets at a lot of questions that we care about. Okay. So here's an example of this. This is from, again, this is still whole rock. This is not from zircon, but they've done this for the Coast Mountain batholith. They've done it for the Sierra Nevadas. And they basically just reconstructed crustal thickness through time using these proxies. Okay, so here's a paper that came out last year, Bellisova et al. 2020. And they have gone into the detrital record and done the same approach. So these are now zircons binned by age groups. And they've done this all over the world. They've just all of the trace element data that was available at the time. They binned and put it in this paper. And so they do this from 4.4 GA, when the first zircons show up in the record, all the way to modern. And they use this lanthanum to terbium ratio to basically make an argument about crustal thickness through time. And they claim that crustal thickness, despite all of the crazy processes that have changed over the past 4.5 billion years, that crustal thickness actually, the melting depth doesn't vary much through time. It's more or less the same across all of Earth's history. You guys can decide whatever you want about that, but it's an interesting approach. Here's a similar approach using the europium anomaly in zircon. I quite like this method because lanthanum is so scarce in zircons, and the europium anomaly is using kind of the middle rare earths, which are much more abundant in zircon. So this is Tang et al. 2020. It's in geology. And so they use that same ratio that we saw before, the lanthanum ytterbium ratio of whole rock, and they correlate it with the mean europium anomaly of zircon. And they show that there's a nice linear trend there. And then they rely on that ratio, that correlation that we saw before between lanthanum ytterbium of whole rock and crustal thickness. And they do the same thing. They do this in Tibet. It's covered up by my box over here, but that's okay. Basically, they show that there's a decent correlation between whole rock values of estimated crustal thickness and zircon values, although there is a strong discrepancy in the Cenozoic there. Those two records diverge. So this isn't flawless, but it's a cool method. So the question was, has anyone tried to do this with comparing it to stable isotopes of like paleo elevation? Talk to Kurt.
They've kind of done the other way, actually. I think it was with the students, when he took the estimated crustal thickness using full rock and then inverted for elevation. And if assuming isostatic balance, you could get an elevation. And there are a lot of, there's a lot more detail than that in the paper. The uncertainties are large, of course. Not everything's in perfect isostatic balance. So you got to model because the Andes. So I'm moving around year for year, but they're not completely isostatic balance all the time. But you can get a rough estimate of paleo elevation. And I can't remember how well it lined up with the stable isotopic record. Stable isotopes are super limited once you get past like the bias. It's overcorrected, but not falls apart. So that's what they took that approach.
And Kurt has a paper in review that deals with trying to reconcile those two records a bit and their discrepancies.
It's up. but it's not.
No,
we don't
no,
have
no.
variation.
Oh, no, I'm talking about your Andy stuff.
Oh,
All right. So we can also use this to say something about ARC processes. This paper, Barth et al. 2013. I'm running low on time, so I'm going to go ahead and speed this up. Basically, they see these magmatic pulses in the tidal record, and they look at the trace elements to basically say something about what is happening during those magmatic pulses. So I'll point you to that paper if you're interested in that kind of stuff. Okay, titanium and zircon thermometry. Mauricio is going to talk a whole lot more about this tomorrow, so I'm not going to get into this too much. Basically, this is what we talked about earlier, where titanium sometimes fits into that silicon site. It's a temperature dependent process. Its ionic radius is not the right size, and so sometimes it fits, sometimes it doesn't. So we can use that to get back at temperature. It assumes that the melt was titanium saturated, a good indicator of just whether rutile is present in the sample or not. Here's an example where they use this on lunar zircon, which is kind of cool. And they basically come through, they filter for unaltered zircon. They do this based on the iron concentration. And then they make an argument about what temperatures it must have crystallized at. And therefore, they make the argument that this melt must have been anhydrous, which is kind of interesting. Well, out of my realm of experience, but. So we talked about this a bit earlier, these thorium-uranium ratios. When we talked about them before, I think I used uranium-thorium, which is why these values have now changed on here. Not for this room. Thank you. So we can use these to say something about whether we think these zircons are going to be igneous or metamorphic. Mauricio will also get into this a bit more tomorrow. But basically, we think the primary idea on what's controlling this is that if we have monazite growing, which is a really common metamorphic mineral, it's going to suck up all of the thorium. So it's going to sequester that, and it's not going to be available for zircon. Okay, finally, a detrital application. This is in the Adriatic 4 deep. They basically have all of these different sources along strike, like 8 different sources. They're all the same age. No way of getting at this. Oh, but wait, there's trace elements. And so they basically make the argument that based on these trace elements that they see in these detrital zircon, the only possible source is 300 kilometers away. And so they have to invoke this large lateral transport along the margin. So it can be really useful for provenance. Okay, I'm going to give the best practices slide in just a second here, but there's so much potential, guys. There's so much here to do. We just need smart people to figure it out. So if you're interested in this kind of stuff, like just start plotting ratios and you'll get a long way by yourself. Okay, so we need to understand the analytical challenges. There are analytical challenges here. We have clear interferences with scandium and aluminum. This is on laser ablation systems. So, you know, 2 of the studies were dependent on those 2 things, so be careful. We need to understand detection limits and standards. As always, run lots of standards, go to a lab that has methods papers, use CL images, analyze grains with interesting ages, normalize your data, all the things that we've heard before. Treat your data well. Okay, that's all I've got. I'm happy to take any questions on trace elements. Do you guys have any idea that we could do so many things with these trace elements? Or is this, yeah? Okay.
Who works with trace elements? Any folks in here? A little bit? Now who wants?
Yeah, come on. Any questions? Completely overwhelmed and stupefied at 5 o'clock. Fair enough. All right. Well, George, I think we'll hand it back to you to wrap up.
Yeah, and I think there's maybe not much need for a long wrap up. I think you guys have seen why we're so excited about geochronology and complementary geochemistry and other methods. As Sarah was just saying, we're just kind of scratching the surface of these new techniques. It comes about because of new instruments that can do new things, the software kinds of tools that Kurt was talking about. I think you can see why we're so excited about the potential of that new kind of style of analysis, getting more quantitative, more statistical. And then using different minerals. Mostly today we've talked about zircon, but as you know, there's a whole range of other minerals out there that have had less study than zircon. So I think maybe more potential for discovery. So I would encourage you to join us tomorrow. I know many of you are signed up for day 2. Day 2 is going to be a little bit different from today, but the same sorts of themes: instruments, applications, different minerals, different geochemical and isotopic systems. It will focus on maybe less igneous and more thermochronology than we've talked about today. So that's going to be an interesting twist. And I guess I'm curious if any of you are planning to be in the room tomorrow, or if you are planning to do this remotely. As you know, the presenters, Mauricio, Pete, and Alan, are not at GSA, and so the presentations are all going to be remote. Maybe you can share with Sarah and Kurt if anybody's planning to be in the room.
It looks like we have 6-ish people planning on being in the room, so I'll plan on setting up in the morning.
Okay, good. That helps us logistically. We will be set up for Q tomorrow. It starts up at 9 o'clock in the morning. We'll be there a little bit beforehand. I hope that's okay, Sarah. Getting things set up, and we'll look forward to seeing you then.
Okay, thanks, George.
Thank you, presenters. You guys did a great job today.
Okay, so tomorrow, 9 a.m. for anyone who wants to be here. If you didn't sign up and you'd like to come join us. The more the merrier. The web link is the same one sent out for day 1. So if you're trying to get on remotely, and we'll make